morning and welcome to lecture 52 in our series of lectures in the Introduction to Wireless and Cellular Communications course. We will quickly review the contents covered in lecture 51 and then focus our attention on the topic for today, which will be primarily on the multiple input, multiple output framework which is widely used in the 4th generation and the 5th generation systems. So, for a quick review of the material covered in the last lecture, the last couple of lectures have been focusing on the topic of multi-user detection, and we have been looking at the 3 different solutions. The first one being the optimal or the maximum likelihood detection, the solution, which is given by the vector B1, which maximizes the metric given in this expression. We said that this would require us to consider all possible combinations of the vector B1, which grows exponentially in complexity. So, therefore, the maximum likelihood receiver is something that would be very complex in terms of implementation when there are large number of users and when the constellation of the signal being transmitted is of a large dimension. On the other hand, we have suboptimal solutions which perform reasonably well in several of the practical scenarios. So, if we have k synchronous users B1 through Bk, each of them have transmitted a symbol. The goal is to identify the received symbol, the transmitted symbol based on the received signal R. The decorrelating receiver gives us a very simple and elegant solution, which says we can compute the receiver transmitted symbols by computing R inverse R and then applying the decision based on this statistic. The MMSE or the Wiener filter, which we discussed in the last lecture, does something very similar. Our goal is to obtain a linear based on a linear transformation of the received vector, the output of the k correlators. If you denote that as R, we want to express the received the B hat as A times R, and we have obtained the best expression for A, which will minimize the error between the decoded symbols and the transmitted symbols. So, that is given by R plus N naught D inverse R and the whole inverse. And this we found was a good way to summarize the 3 different options, the optimal solution, the decorrelating receiver and the MMSE receiver. We also showed how the MMSE receiver, in the case where the noise is not very significant, if we can ignore the noise, actually corresponds to the decorrelating receiver. And in most of the practical scenarios where the noise may not be negligible, then the MMSE would be a better option compared to the decorrelating receiver, because the decorrelating receiver by its structure may cause enhancement of the noise. So, that is a summary of the CDMA multi-user detection schemes, and again I would encourage you to read from the different textbooks and the reference books about the different approaches that we can use for multi-user detection. Now, one of the key points in the derivation of the MMSE solution was the principle of orthogonality. Again, I will just mention it so that we have a good summary of the recap. So, the principle of orthogonality can be explained geometrically in the following fashion. If A is the vector that we are trying to approximate, we are approximating it with the components in the x and y plane. So, the best approximation will be A hat, which corresponds to the point perpendicularly below a perpendicular projection of the point A into the xy plane. So, the best approximation also happens to be the one that produces the minimum error, and geometrically we can see that the point that produces the minimum error will be perpendicular to the components that constitute A hat and to A hat as well. So, the principle of orthogonality states that the optimal solution is one in which the error becomes perpendicular to the input. So, that is the principle of orthogonality, and that helps us simplify the objective function and also derive the expression for the MMSC receiver. So, with this we will conclude our discussion on CDMA, and we will move into our next topic, which is the study of multiple input antennas at the input and multiple antennas at the both at the receiver and at the transmitter. So, in the last lecture we introduced the following diagram, where we have a set of NT transmit antennas. Each of the transmit antennas is transmitting a corresponding symbol x1, x2 to xNT. Notice that each of these antennas are transmitting different symbols. Each of these symbols or transmissions are received by the NR receive antennas, and we are now required to process this information to identify what were the symbols that were transmitted at on the transmitter side. So, we would now like to go into this subject a little bit more in detail. So, again looking at it in the pictorial form and translating it into equations, we can write down the received signal for the first antenna as H11, which represents the transfer function between the first transmitter antenna and the first receive antenna. Likewise, you have the different transmission gains Hij. Hij, the notation would be Hij is the gain or the channel gain from the from the jth transmitter to the ith receiver. Channel gain from transmitter J to receiver I, transmitter J to the receive antenna I. Okay. So, that is the notation that we are following. So, we are now trying to write down all the elements or the components of the signal that is received by antenna 1. So, H12 would be from the second transmit antenna to the first receive antenna. Likewise, all the different NT antennas and their corresponding symbols that they have transmitted. And of course, the receive antenna 1 will have a component of noise, which corresponds to the thermal noise in the receiver electronics. So, if we were to write down for each of the NR receive antennas, then we would get the expression in the form of a matrix, where the dimensions of the matrix are important. We have NR cross 1 receive vector, NT cross 1 transmit vector, and a transfer function matrix which is of dimension NR cross NT. Again, the dimensions are important, so please make note of the dimensions, and the dimensions of the noise vector. Since this corresponds to the receive antennas and there are NR receive antennas, this would also be an NR cross 1 vector that would be. So, as we mentioned in the last lecture, the MIMO problem statement is that we can write down the input output equation for a MIMO system in the following way: y is equal to hx plus n. The MIMO problem statement says, given y, that is, you can observe the outputs of the MIMO system or the received signal vector at the receiver antennas, and assuming that the channel transfer matrix H is completely known between the NT transmit antennas and the NR receive antennas, and we are now required to estimate x. So, this is the problem statement. Maybe a couple of comments that we would like to make even to motivate the topic. Now, as you can see, when we want to detect the signal transmitted by antenna 1 x1, and we are observing the received signal received by antenna 1 y1. So, signal transmitted by antenna 1, signal received by antenna 1. So, basically this is what we are interested in. We find that there are a number of other terms that will interfere in with our observation. So, in other words, a MIMO system is one in which we have the inter antenna interference. So, we have noticed that this could be described as inter-antenna interference. When I am trying to detect the symbol transmitted by antenna 1, I find that the signals from the other antennas are also interfering. However, notice that there are multiple observations in which the contribution of x1 is present. In fact, in each of the NR observations n1 is x1 is present. So, given this environment, what we find is that what we would have considered as an impairment, inter-antenna interference, actually turns out to be to our benefit, because we actually have multiple copies or multiple observations of the transmitted symbol x1 of n. So, in fact, we can make a better and more robust decision regarding x1 of n, while at the same time being able to make robust decisions on each of the different transmitted signals. So, that is the strength of a MIMO system. So, we are able to control or manage the interference such that we are able to make better decisions, or in other words, we are able to get additional performance because of the diversity benefit of the multiple antennas. And so, we are able to improve the performance. And notice we are also at a given time transmitting multiple symbols. So, we are improving or increasing the total capacity of the system. So, in fact, the interference environment is not an impairment, but actually becomes a benefit to us. So, in the case of a MIMO system, what we find is that we are able to increase capacity. So, that is a added benefit that we are able to get. We are also able to improve the performance. So, we are able to get the diversity benefit, and the combination of these two is what makes MIMO systems very interesting, that we can get both improvement in performance and improvement in capacity. Now, where did we pay the price? The receiver now becomes a more complex receiver, because but that is something that we can of course be willing to pay, because we are getting such a significant benefit. So, the receiver complexity goes up. So, at the cost of additional signal processing, we are able to get better capacity and better performance, and that we believe is a very good trade-off in our context, and also our ability to work with these systems. So, given this scenario, now let us see if we can go a little bit further and describe the problem formulation. So, in this context, first we would like to make or clarify or state some of the assumptions that we are making. So, here are assumptions that we are making about the quantities that are in our expression. So, we have an expression y is equal to hx plus n. So, we will have assumptions about the elements of h, the elements of n, and also elements of x. So, we will call it as the assumptions that we are making. So, the first one is the assumptions about the elements of H. Now, as we mentioned, the matrix H is a dimension NR cross NT matrix. It has elements Hij, they represents the complex gains between transmit antenna J to receive antenna I. So, Hij, the elements of the transfer matrix, these are complex values. Hij's are complex, they are also Gaussian, and they are zero mean. Okay. So, complex Gaussian zero mean, therefore, their envelope would be Rayleigh, as we have discussed before, and this is a assumption that each of the channel coefficients are Rayleigh distributed. So, magnitude Hij has a Rayleigh distribution. So, this is a assumption that we are making because we are working in a wireless environment, and we are so basically Rayleigh distribution would mean that there is no line of sight component between the transmitter and receiver, but the received signal envelope has got a Rayleigh distribution. And we also make the assumption that each of those channel gains are independent of each other. So, basically they are independent complex Gaussians with zero mean. So, that is the assumption about the channel matrix. Now, this also corresponds to an important characterization. Such a description of the transfer function basically says that the channel is flat. In other words, the channel gain between the transmit antenna and the receive antenna corresponds to a single coefficient. It is not a transfer function. So, it is not it is a flat fading channel. So, an important classification is that it is a flat fading channel which has got Rayleigh characteristics, and because each of these large number of channel gains are all independent of each other, such an environment is called a rich scattering environment. So, the assumptions that we are making is that we have NT transmit antennas, NR receive antennas, and that it is a rich scattering environment, which means that it encompasses the following: that each of the channel gains is a complex value, it is a flat fading channel, and each of the channels are independent of the other channels. So, that is the summary of the statement that we have. Now, the second statement would be about the noise elements. So, we describe the noise components in each of the receive antennas as white, spectrally white. They are complex. They are complex valued because we are looking at the complex baseband signals. So, they are complex, they are Gaussian and zero mean. So, basically it would be a zero mean AWGN type of environment, additive white Gaussian noise, which is zero mean. So, just as you would characterize the properties of a white noise, basically we can write it down in terms of the correlation matrix or the covariance matrix, which says that if I take the expected value of the vector n times n Hermitian, where the vector n corresponds to the noise terms in each of the NR receive antennas. So, this is n1 of n all the way to nr of n. If this is the vector representing the noise samples, then expected value of n times n Hermitian, because they are complex white Gaussian noise samples and they are uncorrelated with each other, we can write down this expression as sigma n squared times I, the identity matrix, time with the dimensions of that would be nr. So, that would be the description of the noise components. Now, in order for us to do the capacity calculations, we will also make a third assumption. The third assumption is about the characteristics of X. Now, X is the transmitted signal. Typically, in a digital communication system, this would represent a QPSK symbol or a QAM symbol. So, we normally assume that X, the transmitted signal, represents a constellation point in the IQ plane. But for the purposes of capacity calculations, we will also make an assumption which is different from the usual one, but again more from the point of view of capacity calculations. So, we will also make the assumption that X of n, the signal that is transmitted by each of the antennas X of n, is also a Gaussian distributed variable. So, we will assume that X of n is Xi of n is also a complex Gaussian with zero mean and variance sigma x squared. Again, the reason for this will become clear when we talk about the description or the calculation of capacities. So, we have made 3 assumptions, all of which are pointing to Gaussian assumptions. In this equation, the channel gains are complex Gaussian, the received signal noise samples are complex Gaussian, and again the third assumption for the purpose of capacity calculations will be the assumption on X. Now, I would like to go back and re-look at the equation that we have written down. So, the MIMO equation, a MIMO system can be represented in terms of y is equal to h x plus n, and we are told that we have the observations of y and h is known, and we are trying to find out what is x. Now, given this environment, and for a moment if we can ignore the presence of the noise, one possible way for us to do it if h were invertible would be the following. So, one possibility is that you transmit x, possibility 1, that if you received x and you know h, you can do h inverse times y. So, this is what we refer to as channel inversion. Channel inversion. This makes some assumptions. First assumption is that H is a square matrix, and it is invertible matrix, that is, it is non-singular. So, this itself is a fairly restrictive assumption, which tells us that the number of transmit antennas and the number of receive antennas must be the same, and the transfer matrix must be an invertible matrix or a non-singular matrix. So, again we cannot guarantee this in all scenarios, because some of these are random phenomena, and we cannot guarantee this type of an assumption. However, if when you think along these lines, we can also think of a possibility 2, number 2, and the possibility 2 says that you do, before you transmit the signal x, what you can do is you pre-code the transmitted signal. So, basically instead of transmitting x, you transmit h inverse times x. So, at the transmitter itself, we are making a modification of the transmitted signal. So, instead of transmitting x, we are transmitting h inverse times x. Again, this introduces a way of thinking. So, if h is known at the transmitter, and this is what we refer to as CSIT, channel state information at the transmitter, then we can do a pre-coding option. This is what we refer to as a pre-coding. Pre-coding is something that is done at the transmitter with the knowledge of the transmission channel. So, we do h inverse times x, and we call that as x tilde. Now, if x tilde is transmitted, then what I receive will be y is equal to h times x tilde, and this will be nothing but h times h inverse times x, and plus noise, and this would also give me y is equal to x plus the noise. So, in other words, we are able to obtain the received signal as a signal or a decision process where you do not have the effect of the inter-antenna interference. Again, we are able to make a decision independent of the others. Again, this is only under a very limited set of conditions, and when it is H is a square matrix and it is also invertible. Of course, we would be interested in a much larger family of solutions where H is not a square matrix. So, if H is not a square matrix, then what are our options? So, H is a rectangular matrix NR cross NT. The channels, the coefficients of this matrix are complex Gaussians. Now, under this assumption, what are the options that are available? And in fact, it turns out a very general solution can be obtained, which is what we will now derive. So, the result that we are going to be looking at is something that many of you would have studied in the context of linear algebra and in complex variables. This would be the concept of singular value decomposition. Singular value decomposition, again I am assuming that most of you would be familiar with it. So, I will just give a quick overview of the key results that we would need for our discussion, and again I would refer you to any book on linear algebra for the results or for the main elements that we would need for the singular value decomposition. So, the statement of the singular value decomposition states that any rectangular matrix which would fit our description of our matrix H, any rectangular matrix which can be real or complex valued. In our case, it will definitely be complex valued, and so such a matrix A, which is of dimension n cross m, where n and m are different. Now, the statement of the singular value decomposition or the SVD theorem states that the matrix A can be written in the following form, where A can be written as U times sigma times V Hermitian, and we will describe each of the component terms now, where the matrix U is a matrix which is a unitary matrix. So, this is a unitary matrix. Again, the definitions of unitary matrix we have already indicated. So, U is a unitary, U and V are unitary matrices, which is given by the following vectors U1, U2 up to UN. N is the row dimension. So, these are the what are called the left singular vectors. These are the n left singular vectors of A, singular vectors of A, of the matrix A. It also turns out that we can relate these n vectors as the eigenvectors. We can also relate them to the eigenvectors of an n cross n matrix, of a matrix R, which is given by A times A Hermitian. A times A Hermitian, A being n cross m, we can verify that R is a n cross n matrix. It is a positive semi-definite matrix, and using the factorization of a positive semi-definite matrix, we can then obtain the different vectors of U1 through UN. So, the next item that we want to define is the matrix V. V is also a unitary matrix. It consists of the following vectors V1, V2 all the way through Vm. M is the column dimension. These are the m right singular vectors, singular vectors of A, and like before, we can relate these to be related to the eigenvectors of a positive semi-definite matrix. In this case, it is given by R equal to A Hermitian times A. So, if you look at the two variants of one is A Hermitian, this one is A Hermitian A, this would have dimension m cross m, and these would be the eigenvectors corresponding to that. Now, sigma matrix can be written as a diagonal matrix with the following values sigma 1 through sigma L, where sigma k is given by root lambda k, where lambda k can be related to the non-zero eigenvalues, values of A Hermitian, A Hermitian. It can also be related to the non-zero eigenvalues of A Hermitian A. Both of them have the same set of non-zero eigenvalues. So, this can also be related to these. What we have is that the matrix A can be written as U times sigma V Hermitian, where the dimensions we will write down. This is a n cross n matrix, this is a m cross m matrix, this would be an n cross m matrix. So, one of the things is the what is the different, basically we have used a term L, and L is related to the rank of the matrix A, and basically we can make the following statement. So, if you look at our matrix H, this has dimension nr cross nt, and we can make the statement that the rank of H, the rank of the matrix H has to be less than or equal to, the minimum dimension between nt comma nr. Okay. So, this is what we refer to as the dimension L, the rank of the matrix of the So, assuming that we will make the following assumption. Assume that the matrix H is full rank, because we have assumed a rich scattering environment. So, if this case is full rank, then the value L is equal to the minimum of nr comma nt. The rank is, so in other words, let me just say this, the rank this equal to L is less than or equal to in the general case, and when the H is full rank, this is the case. Okay. So, in our case we can have two options. It could be either the case where n is less than or equal to m, where we are looking at the matrix A, which is of dimension n cross m. That means the number of rows is less than the number of columns. In such a case, then the rank would be equal to n, which is the lower dimension. So, in such a case, the matrix sigma can be given in the following form. It would be sigma 1, sigma 2, it is a diagonal matrix all the way to sigma n, and since the number of columns is more than the number of rows, the rest of the entries would be 0. So, this would be the form when n is less than or equal to m. This would be the form that you would get. You would have the n non-zero eigenvalues, which they are represented along the diagonal matrix, and then you have the 0 elements. Now, for the second case where n is greater than m, then now the rank becomes determined by the column dimension m. So, in such a case, the sigma matrix can be visualized in the following form. It is sigma 1, sigma 2 dot 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 all the way to sigma m, that is the column dimension, and since the number of rows is more than the number of columns, what we have for the rest of the entries, it is 0. So, in one case where the number of rows is less than the number of columns, we get the upper form, and in the second case when we have the number of rows more than the number of columns, then we get this form. Now, of course, you can visualize the case where the matrix A is not full rank, in which case there would be minor modifications of this structure, keeping in mind that only a subset of these are non-zero, and we have made the following assumption that the singular values are rank ordered, that is sigma 1 greater than or equal to sigma 2 greater than or equal to sigma n. So, if more of these are become 0 because the rank is not full rank, then the dimensions of the non-zero portion of sigma will reduce and you will get more 0 entries. I would maybe leave that as an exercise for you to look at how this matrix sigma will look like if the matrix is not full rank. But in our case, we will make the assumption that the matrix is full rank. So, the summary of the material that we have presented so far, if you look at the parallel decomposition of a MIMO channel, which is NR cross NT in terms of dimension, that is the task that we have. We assume that we know the following matrix, which is Hij, where I is equal to 1 through NR, J is equal to 1 through NT, that this is known and it is full rank. Okay. So, basically we will assume that this is the problem statement. So, now we can factorize the matrix H in the following way: U times sigma times V Hermitian. So, the MIMO equation now becomes y is equal to Hx plus n. Now, this can be written as U sigma V Hermitian times x plus n. X plus n. So, basically we have submitted the factorized form for this. Now, here comes a very interesting two simple steps which make the MIMO problem statement a very interesting one. So, if I define the vector x, if I define the vector x in the following manner, if I define the vector x to be equal to v times x tilde, or in other words, let me write it in a slightly different way. I would now like to take this vector x, take the vector x pre-multiplied by the matrix V, and we will call that as x tilde. So, a modified input is going to be provided to the channel. So, in other words, we are now going to feed x tilde. So, I have x tilde is going to be fed into the channel matrix H. So, by using the original equation, I will now get a modified output, and the modified output we will call that as y tilde, and y tilde will be H times x tilde plus n. Okay, so, some modified input and modified output to the same equation. So, now substituting for x tilde inside this expression, what we find that this is equal to u times sigma times V Hermitian, x tilde is V times x plus n. So, this is y tilde. So, we know that since V is a unitary matrix, V Hermitian times V is a identity matrix. So, therefore, we can simplify this expression, and one more step that we do if you now say that y is equal to u Hermitian y tilde. So, basically I do a transformation of the received vector, then this comes out to be u Hermitian u times sigma, v Hermitian v I have already dropped, this is remaining is x plus v Hermitian u Hermitian times n, u Hermitian times n. So, that is the expression that we have. Now, notice that u Hermitian u is also a unitary matrix. So, therefore, by unitary matrix property we can that becomes an identity matrix. So, this gives me a result which is y is equal to sigma x plus u Hermitian times n. Okay. Now, we can treat this as a vector n dash, which since u is a unitary matrix has got the same statistical properties as n. So, basically this is a modified noise vector, but notice the rest of the equation is very interesting, because the rest of the equation says that my input and output are related by a diagonal matrix. Sigma is a diagonal matrix. Notice that we have completely removed the presence of the inter-antenna interference. So, the effects of the interaction between the different transmitted signals with the different received signals have been completely removed by means of the two steps. The first one was a transmitter encoding. This was a pre-coding at the transmitter. So, pre-coding at the transmitter, where we did v times x, and then post processing at the receiver, that was obtained at this step. So, this is post processing at the receiver. Now, both of these are very simple steps, both of which are matrix operations based on matrices that are obtained from the singular value decomposition. So, this is post processing at the receiver. So, a simple processing step at the transmitter, a simple processing step at the receiver gives us a very nice and interesting result where we have this expression. So, let us do two things. One is, first let us write down the process that we have done. The pre-processing or the pre-coding that we did at the transmitter, where we said that we will take x tilde is equal to v times x. So, if you were to think of this as a transformation or x1 through xnt, v is this is the matrix V, nt cross nt, that will produce for us the different inputs, the modified inputs x1 tilde all the way to xnt tilde. So, that is what was given to us. Now, this is passed through the channel. This is a channel which is H. So, y tilde is equal to H times x tilde plus the noise, that is represented by these channel elements. So, if you were to connect these, the modified input passing through the channel and the channel producing the outputs y1 tilde to ynr tilde, and then we have the post processing step at the receiver, where we take this and do the following transformation, where we say that y is equal to u Hermitian times x, u Hermitian times y tilde. Okay. So, if this is y tilde, then what we get here are the outputs y1 through ynr, and this is the expression that we have obtained. Again, it is a very powerful result. This is something that we will use repeatedly in our discussion. So, we will write it in the following form: y is equal to the post processing step U Hermitian, the channel which is U sigma V Hermitian, this is the channel, times the pre-coded transmitter which is V times X. So, this is the, and of course, we have the noise element that is being added. So, this is the post processing step, this is the pre-processing one. So, this becomes the pre-coding X tilde, this is my channel H. So, X tilde passing through the channel H produces the output Y tilde, this whole thing is Y tilde, and that you do a post processing at the receiver which is U Hermitian times Y. That becomes the final step where this becomes equal to the vector Y. Okay. So, interesting way to visualize it. It is a transmission that is from NT transmit antennas to NR receive antennas. That is the original structure, but we have split the transmission process into a pre-coding step, the MIMO channel followed by a post processing step, and this is a good way to visualize it. Now, another interesting way to draw this figure, and I believe that gives us a lot of insight, and what we would like to do is look at how we can represent this. So, the parallel decomposition of a MIMO channel, parallel decomposition can be captured in the following form: parallel decomposition. So, we have NT transmit antennas and we have NR transmit antennas, but effectively the number of channels, the parallel channels that we have depends on the rank of the matrix. Now, let the rank be equal to L, the rank of H equal to L. Now, once we have done the parallel decomposition, then what we can say is the parallel decomposition of the channel looks like this. Okay. There are only L transmit antennas, because effectively there are L parallel channels. We can call this as X1 tilde, X2 tilde, XL tilde. Now, this will get transmitted by this antenna, and effectively the channel looks like a gain for each antenna which is different. So, for example, the first antenna experiences a gain which is proportional to sigma 1. So, think of the gain as a multiplicative term which is represented by sigma 1. This signal now has a multiplicative factor sigma 2, and the Lth antenna has got a multiplicative gain which is given by sigma L. Okay. So, each of these we are looking at the parallel transmissions. So, there are L parallel transmissions, and the parallel transmissions have got a diagonal gain which is sigma 1 through sigma L, which is what we are trying to capture in our diagram here. Now, of course, in any transmission system there will be the additive noise. So, this one we get a noise term N1. Second branch we get a noise term N2, and the third and the last branch we get a noise term NL. Now, this comes out at the receiver, and this is what is picked up by the receive antennas, Okay. So, the number of receive antennas is also equal to L. This is receive antenna number 1, number 2, and the last one is number L, and the signals that we obtain are Y1 tilde, Y1 tilde, Y2 tilde, and all the way to YL tilde. So, the parallel decomposition can be visualized in two ways. One is the matrix representation that we have shown in this figure. The second way is to think of it as parallel channels, where the transmitted signals x1 through xl are experiencing different gains, and the noise terms, notice that the noise terms are all additive white Gaussian noise terms with the same variance, so and the received signal. So, this, if you were to describe it in equivalent form, consists of L parallel channels. Let us write it down. There are L parallel channels. The noise variance in each of these. So, each of them has got equal noise variance. Each of the noise terms is sigma n squared. So, each of them have got the same noise variance, but each of them have got different channel gains. And if we have ordered our singular values such that sigma 1 greater than or equal to sigma 2 all the way to sigma L, then what we find is that we have L parallel channels where each of the channels has got different signal to noise ratio. Notice that sigma 1 is a gain for the signal on channel 1. So, there are L channels, each of the L channels have different signal to noise ratios, SNRs. So, SNR of channel 1 will be better than or equal to SNR of channel 2, better than or equal to SNR of the channel L. So, this is what we have as our ordering of the channels. So, to summarize, we have a MIMO system. Where we can represent the input output by means of a transfer matrix. We have explained the assumptions that we have made regarding the entries of this matrix. The next step was to the assumptions. Then we did the singular value decomposition. The singular value decomposition tells us that any rectangular matrix, whether it is real or complex, in our case it is a complex valued matrix, can be decomposed in the form U sigma V Hermitian, and the expressions for the U, V and sigma were obtained. Based on that, we showed what the structure of sigma would be depending upon whether you had the number of rows greater than the number of columns or vice versa. Then finally, we can write down the expressions and we can show that the SVD decomposition can be captured very nicely using matrix form or in terms of a parallel decomposition form. Now, notice that once you have done the parallel decomposition, it is also easy for us, because each of these channels has got a corresponding SNR. We can of course calculate the channel capacities, because we know that the capacity is related to the SNR of the channel. So, the beauty of the SVD process is that it has now enabled us to do the separation of the channels into parallel channels. However, keep in mind that one of the key assumptions that we have made in the obtaining the parallel decomposition, again maybe we should write it down. It is a very important assumption that we have made, and that is that the transmitter knows the channel, CSIT, or at least it knows what it needs to do to obtain the matrix V Hermitian. So, because that is what is required at the it requires knowledge of the matrix V, so that it can do the pre-coding. So, under this assumption we have obtained a very nice result. Now, we obviously have to ask the question, what if the transmitter does not know the matrix V, which is based on the singular value decomposition, or it does not have the CSIT. So, obviously we are interested in those situations where this information is not known to the transmitter. So, we would like to get a understanding of what could be done in such a situation when you do not have the ability to do the pre-processing. What would be the understanding of capacity in such a situation? So, in that regard, we will now study, or in the next chapter, next lecture, we will be studying an important element which represents, which pertains to our understanding of the concept of entropy. This is the same as the entropy that we would discuss in information theory. So, what we would like to do is get a understanding or review the basic concepts and see how the understanding of the concept of entropy can help us in understanding the capacity of a MIMO channel. So, capacity of a MIMO channel based on our understanding of the capacity or the concept of entropy. That will be the content of the next lecture. So, please do review the material that we have covered today, and we will pick it up from here in the next lecture. Thank you very much.